Okay, I think we can start. So thank you very much, everyone, for coming to our webinar today, and thanks to HiPEAC for giving us this opportunity. I'm going to go through the agenda very quickly before we begin. So I'm Nicoleta Chiapidou. I'm the leader of the class dissemination from the Barcelona Supercomputing Center, or BSC. So I will be chairing the session today. And here you can see our agenda. We will begin with the presentation of Eduardo Quiñones, the class project coordinator from BSC. He will present the class project, give an overview of the class software architecture. We will go ahead with the presentation of Eli Kartsakli, senior researcher at BSC. Eli will talk about the distribution and orchestration of real-time analytic workflows over the heterogeneous distributed infrastructure within the class project. And then Ruth Palmero, the project coordinator at Atos. Ruth will talk about the deployment and life cycle management of containerized applications through Rotterdam within class. And then Ereth Haddad, a research staff member from IBM at Haifa. Ereth will talk about the class analytics fabric. And finally, Roberto Caviccioli, researcher at Unimore. Roberto will talk about the class software architecture, edge analytics, and use cases. And then we will have some time for questions and answers. And during the presentations, we will have everyone muted. I mean, all the attendees muted, but you will be able to ask any questions you would like in the chat feature of Zoom. So please go ahead and write your questions there. I will be monitoring these throughout the webinar. And then during the Q&A, we will have the opportunity to have a discussion. And yeah, as I said, feel free to ask your questions in the chat. And also just to let you know that we are recording this webinar, and the full recording will be posted on the HiPEAC website as well as on our class project website afterwards. And I think that's from my side. We can go ahead with Edu's presentation. So I will stop sharing now and I will give the floor to Edu.
Thank you, Nicoleta, for a presentation. Okay, so let's start with the overview of the class project, and specifically on what are we intended to do in the class project, that is the development of the software architecture, of the class software architecture. Let me first start with just some very brief information about the class project. Class stands from Edge and Cloud Computation and Highly Distributed Software Architecture for Big Data Analytics. It is a European project under the scope of the ICT 16/2017. It is a research and innovation action. The total duration of the project is 42 months, starting January 2018. This means that the project is about to finish, and the budget is about 4 million. And this is the group, the picture of the team without wearing face mask, which is always good to see it. Okay, so let's then start with a motivation. So why we think the research that is being done in class is important. So in the, let's say, traditional data analytics environments or platforms, all the intelligence, it's mostly at the cloud level. Why is that? Because in the cloud is where the computation muscle is. is where it has the large data sets, is where the high computation capabilities are. And so there is where the intelligence is. While at the edge level, traditionally there is some very little intelligence, and it is mainly to collect data, filter data, and then transfer this data. Typically, we refer to the analytics that occurs at the cloud, data at rest analytics, and analytics that occur at the edge level are named data in motion. However, this scheme, this scenario, is not valid anymore for a number of reasons. The first one is that the data sources, it's more and more geographically distributed. And this poses a lot of challenges regarding data analytics, as well as how all this information flows to the cloud computing. And the perfect example is the smart city use case. The second case is that more and more this type of systems not only needs to fulfill the functional correctness of the system, but also there are other non-functional requirements that needs to be taken into account, and especially real time. More and more this type of systems are reactive systems in which there is a specific time budget in which the system needs to respond. And this is specifically, and this is, for example, an important requirement in the mobility domain, in which cars, vehicles are expecting an answer from outside in order to react to a given event. And then, of course, there is the traditional 3V challenge, in which there is an increment on the volume, on the variety, and the velocity of the data sets. Overall, this scenario in which we have very differentiated cloud computing and edge computing environments does not scale, and so we need to go for a more combined scenario in which the edge and cloud are truly coordinated. So rather than having analytics at the cloud level, we have analytics across what we call the compute continuum. And this is exactly what class is about. Class is about how we can increase the capabilities of data analytics of system by effectively combining cloud computing and edge computing, and being able to develop, deploy, and execute complex data analytics workflows across this compute continuum. So we can take benefit of both data in motion and data at rest analytics into a single system. One of the key innovations of the class project is that it also takes into account the fulfillment of the real-time requirements. This means that we are providing, we are guaranteeing the response time of this workflow, so the system can take the response of, or can guarantee the response of the system within a given time budget. And in order to provide this, one of the key elements that we need to incorporate it is the use of parallel and energy efficiency embedded platforms and at the edge side. And here we are experimented with platforms using EPUs in order to accelerate AI operations. And if there is a word that somehow describe what are we addressing in class is productivity. So class is about increasing the productivity of the development of data analytics workflows executed across the compute continuum from 3 different angles. So we want to enhance programmability. So we want to provide an API in which the parameter is doesn't need to know any detail, any knowledge about the underlying platform. So we are abstracting the complexity of the underlying compute continuum. We are also addressing portability and scalability. So we want our system to be able to be executed in different platforms, and of course, performance. Performance and guaranteed performance. And so how are we going to provide this? So the way class is implementing its vision is by developing a software architecture, the class software architecture. And one of the innovations of the class project is that it takes technologies from different computing domains and combine them into a single framework, into a single development framework. So on one side, we have an API that allows to distribute distribute advanced and complex data analytics methods across the compute continuum. We also have technologies that supports both serverless and container as a service cloud technologies. We are using orchestration methods that allows to deploy, distribute, and execute workflows in a time predictable manner, so we can provide a given time budget in which workflows are going to be executed. And then very important, we are taking benefit of the most advanced embedded parallel heterogeneous processor architectures at the edge level to provide at the edge level the level of the level of performance that is needed. And in this case, we are using parallel programming models that are used in HPC, like for example, OpenMP, like CUDA, or for example, we are also other type of tools like OpenCV. So during this presentation, during the rest of the presentation, we will be focusing on the different technologies and presenting each of the tools for a serverless support, as it is the case of Ethops, for container as a service support, as it is the case of Rotterdam, both Lithops and Rotterdam being executed on top of Kubernetes, for the distribution, for the orchestration of workflows and the distribution of the data storage. We are considering COMS and AttackLay, and as I said before, for exploiting the performance of the edge platforms, we are using OpenMP and CUDA combined with OpenCV. And so one of the most challenging things we are dealing in the class project is that we want to test our software architecture in a realistic smart city use case. So on one side, the software architecture is going to be deployed in what it is called the Modena Automotive Smart Area in the city of Modena in Italy. That it is a real living lab urban area that provides connectivity and provides computing e-sources, IoT and IoT devices in order to exchange information. And we also have 3 connected cars that are equipped with different sensors and B2I communication in order to collect information as well and distribute it and share this information with the city. And this is exactly what it is class about. Is about to use the software architecture, so the information that is collected from the sensors of the city, mainly cameras, and the information collected by the cars, because the cars can be seen, in fact, as a mobile sensor. This information can be combined to generate a knowledge upon which we implement 2 use cases, 2 main use cases. The first use case is the computation of what are the level of pollution that the different vehicles emit in real time. And here, the innovation of this use case is that we can detect, we can provide this estimation of the emission at the level of the vehicle, so we can provide a much more precise estimation about the pollution. And then the second use case is we want to enhance the advanced driving system assistance of the system by combining the information from the vehicles with the information from the city, so we can enlarge the sensing capabilities of the vehicles and see what we call behind the building. So the vehicles can understand and see behind the buildings. And here we have 2, let's say, sub-use cases that what we call is the virtual mirror. With as I was saying before, the vehicle can see what's behind, and also 2 sources of attention, which means while the driver is looking at one side, we have the information from the city and from the vehicle that complements the vision of a driver from another side. And here, in the case of the advanced driving assistance systems, is where the real time is important. And just let me very briefly provide or describe one of the use cases. Okay, so you can have a better understanding of what are the capabilities that our software architecture is intended to implement, and it is in fact providing. So let's assume, for example, that we have a vehicle that is approaching a crosswalk, but there is a truck that is preventing the vehicle to properly see this crosswalk. But at the same time, there are 2 cameras in the city that are pointing to this crosswalk and can detect if there is a pedestrian crossing. Here you have a schematic view of this situation. So in order to detect, identify, and determine if there is going to be a potential collision or not, there are a set of data analytics methods that we need to implement and combine them. This is what we call the data analytics workflow. So from the cameras, we need to detect the pedestrian, track the trajectory of the pedestrian, combine or determine if the same pedestrian is seen by the 2 cameras, generate the knowledge, and then based on this, we can compute the trajectory, determine the collision, and if this is the case, inform the vehicle. At the same time, the vehicle is also going to implement sensor fusion algorithms that is going to be combined with the information collected from the city and include all this information into the knowledge base. So the trajectory prediction and collision detection can have a complete knowledge about the scenario. What the class software architecture is providing to us, the first of all, is an API that allows us to easily describe this workflow. This workflow needs to be executed in the computing infrastructure that the city provides. So let's assume that let's consider that the city includes some edge and fog computing resources as well as a private cloud. And this is the distribution, and this is let's say the most optimal distribution of this data workload. What tools are going to provide this distribution? The class of architecture. So we are going to have, as I was saying before, an orchestration that is going to schedule, deploy, and execute the different analytics across the compute continuum. At the cloud level, we are going to have serverless functions that are going to be mapped, that are going to implement map-reduce operations in order to speed up the computation of the computation of the trajectory prediction and collision detection of the different computing elements. We are going to have a container as a service responsible of scaling in and out the different computing resources at the cloud level, taking into account time predictabilities, all with the objective of informing to the card about a C2 a scenario that can be potentially of risk. And this is more being a bit more precise, is what are the computing and communication infrastructure that the class use case is having access to, and how the different components of the software architecture of this class software architecture is used and executed in order to provide the type of features we want to provide to the developers. So we are going to have smart cars. We're going to have 3 smart cars plus some connected cars with 4G connectivities. We are going to have a set of cameras in this surrounding area. We have 16 cameras that are connected to 4 computing nodes in which the computation is going to be distributed, and plus a private cloud in infrastructure in which the most computationally intensive data analytics are going to be offloaded. And just to conclude my talk, one of the objectives of the class project is to develop a software architecture that is going to allow developers to describe complex data analytics workflows in which data motion and data address analytics can be combined, with the objective of increase the productivity of the development of these systems while guarantee the real-time properties that are inherited from the application domain. And we are going to test, the class is testing the software architecture in a very challenging use case, a real smart city use case composed of a distributed sensing and computing infrastructure in which we are going to implement a set of urban mobility application. And that's all from my side. Thank you very much.
Thank you. Thanks very much, Edu, for your presentation and giving us the overview of the class project. And I think we can continue with the presentation of Eli Karsakli now. Eli, we give the floor to you. You can share your screen.
Hi, Nicoleta and everyone. Just let me see the screen. So can you see my screen?
Yes, perfect.
Okay, so I want to continue from where Eduardo left. and describe the framework that we use in class for the distribution and orchestration of the real-time analytics over the heterogeneous and distributed infrastructures. So to begin with, I would like first to describe the challenges that we face in such distributed edge and cloud ecosystems as the ones that we consider in class. So of course, distributed computing is not a new term. It has been around for quite a time and refers to the execution of workflows over a network of systems that share resources as a pool. However, now with the advances in telecommunications, networking, cloud computing, and the rise of many real-time services, we have been reaching a new paradigm that is edge computing, that is closely related also to the cloud computing. So this is what we have. We usually have a layer of IoT and connected smart devices, such as smart sensors, actuators, smart cameras, and also connected devices such as smartphones and connected vehicles that are that can be heavily sensorized. And this layer generates a vast amount of data that can be processed to provide very interesting real-time services. Nevertheless, even though some of these devices have some computational capacity, we usually need extra computation in order to really process the data and provide helpful services. So this is where edge computing comes in play, because we want to have the processing of this data as close to where the data is generated to keep the response times low. So we have this edge computing layer here that can handle this computation. Nevertheless, the resources at the edge computing layer are usually limited, so we still need to offload heavy computational tasks that are not so latency constrained to the cloud. So here in class, we see all this pool of resources as the compute continuum that spans from the edge to the cloud. And we want to provide the application developer with the tools to build applications that can fully exploit the whole compute continuum and distribute the tasks there while providing real-time services. So what are the challenges that we face? First of all, as Eduardo mentioned before, we have a massive volume of data that is generated through geographically dispersed sources. In class in particular, we have a network of smart cameras and a fleet of connected vehicles. Then we have heterogeneous networking connecting all the computing resources. And this means that different technologies might be used for the interconnection of the devices. And these technologies have different capabilities and different requirements and restrictions, for example, in terms of throughput, reliability, etc. And this is very important because if we care about real-time services, the communication delay introduced by the networking is a considerable component of the response time. Finally, we have heterogeneous computing infrastructures in terms, for example, of architecture, where CPUs or GPUs could be used. In terms of processing power, where we can have from very powerful cloud servers to Raspberry Pis, for example, and different execution environments that we can have different operating systems, virtual machines, containers, etc. So the question is, how can an application developer build an application, a service that can run over this whole a highly heterogeneous architecture and still provide real-time guarantees? So even though we have the concept of microservices that decompose services into smaller components that can be executed in different places, still we have the problem of where distributing each component. So here in class, the solution we propose for the computation distribution is through the use of the COMS framework. So COMS is an open source framework developed by BSc for the development and execution of applications over distributed infrastructures. So it has two main features, the programming model and the runtime system. So if you go to the COMS webpage, you can find a list of strengths and advantages of this framework, but I will only mention the three most relevant ones. So the first one is that it enables the distribution and parallel execution of workflows through a programming paradigm that is very close to sequential. So we can have an application written in Python, Java, or C, and with some minor modifications, we can convert it to a comms workflow that can be distributed. Then it is agnostic of the underlying infrastructure. And with this, we mean that, of course, we have to define the available resources at the compute continuum, or provide a mechanism to discover the available resources in runtime. But once this is done, comms will handle the distribution and the orchestration of workflows in an automatic way, which is transparent to the programmer. Finally, comms is seamlessly integrated with DataClay, which is a distributed data store that can handle the transfer of data wherever it is needed for the computation. So to better understand this, I will show an example. So I will show how we can develop an object detection application with a comms framework. So the example I will share is a simplified version of the workflow that we actually use in the comms use case of assisted driving that Edu presented. So let's assume we have a camera that is pointed in this intersection here in the MASA area in Modena. So what we want to do is detect all the objects that are captured by the camera and track them. And then create a data model that contains snapshot that for each frame, it contains the information about the objects that are present, their ID, their position, their velocity, etc. And create this snapshot data objects. Now, in the actual class use case, it is a bit more complex because we have multiple cameras and also data captured from smart vehicles. So we need to deduplicate this data in order to remove the duplicate identification of the same object. And we also federate the snapshots created to the cloud in order to be used by more complex analytic applications that will, such as trajectory prediction and collision detection, that will be mentioned by my colleagues later on. So let's focus in this simplest example. So how do we start making this application? First, we write the sequential code. So for each of these logical blocks of this workflow, we define the different functions. For example, first we have to get the detected objects by connecting to the cameras and applying a deep neural network, which will return the bounding boxes of all the detected objects. Then we use this information within a tracker whose work is to get all the detected objects, see if these objects were present in previous frames, and if yes, assign the same ID, otherwise assign them a new ID as new objects, and then extract useful information such as the actual position of the objects and their velocity, etc., by correlating the position in the pixels with the actual GPS position. Then in case we have more data sources, we apply the duplication. And finally, we create the data model and the snapshots. So the main function will look like this. We could have an infinite loop or iterations, where for each of the available data sources, we get the detected objects, we track them, and once we have all the tracked objects for a given time, timestamp, we deduplicate them and create a snapshot. Now, if we execute this code, it will process each frame captured by the camera in a sequential manner in one resource. So how do we convert it in a distributed workflow? So by using comms, we simply need to annotate the tasks that are to be distributed with this task decorator and also identify their dependencies. So we go back to the function definition and add these descriptors here. And for example, for the tracker, we identify as dependency the detected objects passed by the deep neural network, and also a list of tracked objects from the previous frame, in order to check if the new detected objects are actually new or if they were present in previous video captures. And then, for example, the input of the deduplicator should be all the tracker lists available referring to the same time frame, so timestamp. So this is a collection of lists. So furthermore, if we have any hardware constraints, we can also mark them with this decorator here. For instance, if we want to force that the creation of the data model takes place in a specific node called aggregator node, we can mark it with this decorator here. So what happens next? In the runtime, COBS will create the task dependency graph. So in this example, the graph would look like this. We would have the different nodes corresponding to a different function, and this would be the dependencies. For example, this would be the object detection of the second frame that comes after the first. This would be the tracker that needs also information from the previous tracker, etc. And the advantage here is that we can process the frames in parallel. We can exploit the parallelism of this workflow. Because even, for instance, if the deduplicator or the snapshot creation take a lot of time, we can still continue with the workflow and start processing the next frame. So even though this may look simple, in the actual use case, if, for example, we process 1 second of video frames, that would correspond to approximately 30 frames per second, the workflow would transform to this, which is fairly more complex. And in class, we don't only process videos from a single camera, but we will have up to 16 cameras providing live video streams and will be processed by the same 4 fog nodes at the same time. So you can see that the task dependency graphs become fairly complicated. And the advantage of COMS is that all the distribution of all these generated tasks happens in a way transparent to the programmer. So COMS will tackle all the distribution of all these tasks. So how does this work? COMS has a master and worker architecture. So if we consider this infrastructure here that is very close to the actual infrastructure that we have in MASA, in the MASA area in Modena, let's say we have an aggregator node and 2 different fog nodes where computation can take place. And one of the fog nodes is connected to the camera. So if we deploy the COMS master here at the aggregator node, the first thing to do would be for the master to deploy the workers. So in our example, 3 workers are deployed, one at each of the fog nodes. And then at runtime, the master will run the main function, create the tasks and distribute them to the workflow, to the different workers based on some scheduling policy. So in this example, let's assume that the detection and tracking tasks are assigned to fog node 1 that is closer to the camera where the data is generated. The snapshot creation was hard bounded to be executed at the aggregator node through this constraint decorator. And for example, the deduplication tasks were assigned to fog node 2. The COMS also will handle the transfer of data wherever they are needed for computation. And with this, we mean that if, for example, the deduplicator needs the input of all the trackers, COMS will automatically handle the transfer of this data where the computation will take place at fog node 2. And the transfer of this data can happen, since we know a priori where the task will be executed, this can happen in parallel with computation. So what are the scheduling policies that we mentioned about? Well, COMS comes with some baseline scheduling modes such as FIFO, but for class, since we care about the real-time properties of the system, we have implemented a new workflow orchestrator. So the first thing that we do is that we proceed to make an offline profiling of the available compute continuum in order to measure the task execution times and the data transfer times. So as part of the response time, it is very important that we take into account both the computational latency and the communication latency. So once we have this profiling, the workflow orchestrator maps the available tasks, the created tasks, to the available resources with the objective of minimizing the response time. So we have developed a number of different policies. First, we have an optimal but computationally intensive policy that is through mixed integer linear programming. And we also developed some heuristics that are close to optimal, but are more tractable in runtime. The key here is that we define scheduling iterations. And with this, we mean that we generate the workflow for a number, for example, we handle the processing of a given number of frames, let's say 100 frames or whatever. So for each iteration cycle, we generate the whole task dependency graph and distribute it to the available resources based on the scheduling policy. And the advantage of this approach is that it enables us to retrieve, to calculate response time upper bounds. And this is very important because it allows us to provide real-time quality of service guarantees. Now, from one iteration cycle to the other, we can go and have reallocation of resources that is triggered when either we detect changes in the compute continuum, for example, some resources are down or new resources are discovered, or when the real-time properties are not met, if for some reason deadlines of tasks are missed repeatedly. So we need to reallocate the resources. Now, this is a very brief example. Following up the example we presented before, if for some reason the fog node is down or the tasks are executed with extreme latency that violates all the deadlines that we calculated, then comms will automatically take these tasks and redeploy them elsewhere. For example, they will go to fog node 1 or fog node the aggregator node. Another feature that I would like to briefly mention is that comms can also deploy workers on the fly at the cloud. And this is done in class by making communication with the Rotterdam container as a service. And now this will be presented in more detail in the next talk by my colleague Ruth. But the idea is that if more resources are needed, the comms master can request for them at Rotterdam, and then a number of workers will be deployed and scaled in or out automatically using Kubernetes, a Kubernetes cluster. So we don't use this in the application I described earlier, because for the real-time object detection, we want to keep the computation at the edge, but we use them in the different use case of the calculation of air pollution emissions. So concluding, we have seen how the class software architecture can manage the distribution of complex analytic workflows over the compute continuum and in a way that is transparent to the programmer and agnostic of the infrastructure. And we have also seen how through the workflow orchestrator, we can obtain real-time guarantees provisioning, and we can also handle the reallocation and scheduling on the fly of the resources in order to meet the real-time requirements. So that's all for me. And thank you very much.
Thanks very much, Ellie. Thank you. That was great. So now it's the turn of Ruth Palmero from Atos. So I give the floor to Ruth. You can share your slides, Ruth, whenever you're ready.
Hello, can you see my screen and hear me?
Yes, we can hear you and see your screen, but it's not presentation mode yet. Now, yes, okay.
Okay, so thank you everybody for attending this webinar. I will talk about the deployment and lifecycle management of containerized application with Rotterdam. So we will talk about Rotterdam Computer as a Service component that is part of the class continuum, computing continuum. Also, we'll see how we use the SLA Lite to enforce the quality of services, and how we have improved the SLA Lite with an SLA predictor that help us to fulfill the real-time guarantees that are so important in this class project. So we have the class cloud computing platform installed in Modena Data Center. We have two clusters that are private clouds. One is an OpenShift cluster, the other one is a Kubernetes cluster. Our Rotterdam Computer as a Service system is running in the Kubernetes cluster. It is able of deploying and following all the life cycle of applications or comps workflows from a very simple definition, a JSON definition file. You can instantiate a configuration, and also the application and all the developers can identify quality of services metrics that they want to enforce. So it can also, from the supervision of this quality of service metrics that is being done by the SLA Lite, maybe Rotterdam can decide that it can escalate the application to a different cluster, or even it also has capabilities to run in the edge on different infrastructures. So more precisely, Rotterdam is a computer as a service that allows the deployment and management of containerized application from the Modena data center Kubernetes cluster, and in the context of class, it is able to run COMS workflows. It supports different infrastructures like Kubernetes, OpenShift. Also, micro Kubernetes can also run other than COMS workflows. Can run a normal application. It can run serverless functions, and this is all supervised by a single Rotterdam instance in the cloud or in the edge. Thanks to the SLA Lite, that is a part, or it's an independent component that is connected with Rotterdam. It provides the application, the scalability and elasticity can be triggered by specific quality of service rules that are defined by the user. All this is very simply the communication with Rotterdam is simple, with a JSON format that describes the application that needs to be containerized and deployed, or the workflow, or the serverless functions, together with the quality of services. And the communication is also through a REST API. So this is an example of the Rotterdam REST API. This is those will be the entry points to create, delete, consult the state of the different tasks that are running on the supervision of Rotterdam. Yeah, here are two examples of the JSON file that we were mentioning. The first one is an example of a COMS workflow. The second one is a serverless function. Let's focus on the first example. We see that we have a very simple structure in which we only need to identify the number of replicas that we want to initially run when we deploy the workflow, and also the quality of service. The quality of service is identified by an ID, is a template, and we also need the image of that needs to be containerized. So as you can see, from the application that communicates with Rotterdam, in this case it will be COMS, there is no need to know what is the infrastructure underneath to run this application. Just to say that the replica in the context of a COMS workflow will be the workers. The concept of workers has been already been specified, described by Ellie in the previous presentation. So from this JSON file that is received by Rotterdam using the REST API to develop a new infrastructure, the SLA Lite, that is going to be the one supervising that the quality of service is being met, will create an SLA agreement, a service levels agreement. So from the name of the template or the quality of service ID that it received from the Rotterdam, from the JSON file, it will obtain all the information of what is the metric that is going to be surveyed and what is the specific constraint that needs to be applied. And also what is going to be the action when this constraint is not being met. So what is this SLA agreement means? It means that the deadline misses is going to be the metric that is going to be supervised. This is a metric that is being provided by the COMS workflow through Prometheus monitoring in the case of a class. So when this constraint is not being met, the action is going to be taken. It means that the action is going to be escalation of the number of workers. So from 4 replicas, we will pass to 6, multiplied by the scale factor. So this is the information, and this is all the time the SLA is going to be supervising that the constraints are being missed. Deadline misses is actually a measure of, it's a time warranty measure, actually. So initially, the COMS master will send to Rotterdam the JSON file with the information of the deployment, the one that we have just seen, and at the same time, it's going to start pushing the metrics, the deadline missing metrics, to the Prometheus. SLA Lite is going to supervise all the time. So the initial infrastructure that is going to be, the initial deployment is going to be with 4 workers. Yeah, but at a certain point, this deadline missing is not going to be met. That means the final execution time is supposed to not to be achieved. So there's a violation that the SLA is going to communicate to Rotterdam, and Rotterdam will scale up to 6 workers. What we have identified in some of our experiments is that this scalability, or this increase in the number of workers, sometimes it produces an overhead time that doesn't permit us to fulfill the time warranties. So what if we could predict what is the optimal number of workers from the initial point, and we avoid having to scale even though we have this possibility. So for this, we have developed a new module that is our SLA predictor, in order to make sure that we fulfill these real-time warranties that are so important in our class project. Yeah, the SLA predictor is actually machine learning, is a model that is connecting with the SLA manager. So our JSON has changed a little bit. Actually, the quality of service is not going to be a deadline missing anymore, but we are going to take the value of execution time. That is actually from this value, from this execution time value, the deadline missing was created. So actually, it's a very similar quality of service measurement. So we obtain, when we receive the JSON file with the const workflow specification, the same number of replica, but instead of the deadline missing, we will receive the value of the maximum execution time. Okay, and with this information, before creating the SLA agreement, the SLA manager will query the SLA predictor with the number of workers and the specific time, and the SLA predictor will respond with the optimal number of workers that in this example was 6 instead of 4. So from the beginning, the deployment will be done with 6 workers instead of 4. So let's talk a little bit of how we have designed the SLA predictor. Okay, we have done first phase of exploratory data analysis, in which we have classified the state of the system, the state of the cluster in the Modena data center as being of a low, normal, or high execution or load, and we have taken as training data real execution, where we know the label, we were labeled with the real number of workers and the real final execution time. And with of that, we have used finally we have decided that the most convenient was a classification model. So SLA predictor will take the last hour of the state of the metrics in the last hour of execution for these metrics that define our system. It will define what is the actual stress of the system, either low, normal, or high, and from this information, when it receives a query with the number of workers, it can predict if the execution time is going to be met or not, and if not, decide of a better metric, of a better number of workers to respond with. So, well, just as a summary, we have described how Rotterdam can help us in the deployment and lifecycle management of containerized applications. It's a tool that it can work on multiple infrastructure, micro Kubernetes, kubeless, both in cloud and edge. It is easily connected with a REST API with the rest of the class software systems, and it only needs a very simple JSON format to describe the applications, and also to describe the quality of rules that needs to be defined in the execution of the applications. And we also have defined the SLA predictor that help us trigger inform quality of service violations, so that the quality of service is the actions to fulfill the quality of service, to enforce the quality of service, is being informed by a machine learning model. And we have also described a little bit how we have defined it and designed this SLA predictor. And well, that's all from my side. Thank you very much.
Thanks very much, Ruth, for your presentation and this very useful summary in the end. Thank you. So I think we can move on with the next presentation by Ereth Haddad from IBM Research HiPEAC. Ereth, when you're ready.
Hi, do you see my screen now?
Yeah.
Okay, so let's go.
Okay.
Hi everyone, I'm Erez from IBM HiPEAC, and I will talk about the class analytics fabric. This is a general view of the collision avoidance workflow implemented in class, which highlights the involved analytics. So first of all, you can see I will start going from right to left. You see on the right side, you see the car, so one of the cars, that is instrumented with sensors, and that car, as Edu explained, performs computation on board the sensor fusion and sends the resulting data to the class infrastructure. The same goes to the static sensors, the smart cameras. Can everybody see my cursor? Okay.
Yes.
So okay, good. So the smart cameras are also executing analytics and both data coming from the car and from the static cameras is actually converted by analytics to a stream of objects to that are anonymized and are symbolic, so that a car is just represented as a car, a pedestrian as a pedestrian, and they are being tracked. Now, next, for each of these objects, a history is being built based on recurring detections, and based on this history, we can predict a future trajectory of that object. This is another analytics computation. That's trajectory computation, and then the final step of this workflow is based on the predicted trajectories. We predict possible collisions between these objects, and if a collision is indeed predicted, a collision warning is sent back to the respective cars. So as you can see, there are quite a few analytics components involved. Now, to that end, we have implemented an analytics fabric inside class that allows different applications to coexist and interact and even send data to one another and invoke one another. It's based on a serverless infrastructure. We use Apache OpenWhisk. Basically, it's an event-driven infrastructure that allows various types of events, including direct invocations, but also message reception, sensor data, user input, or timer data, timer triggers, to cause invocation of various analytics backends. We have quite a few of them, as you can see, deployed, including comps, which has already been presented by Ellie, and there is lithops by IBM. There is the neural network by Unimore and by Atos, and additional components. All of them, everything, of course, is running on top of the foundation of comps and data clay, as Edu and Ellie presented. So before I'm going to discuss the value of serverless in class, I'm going to give a brief, very quick introduction to what serverless is, in case some of the attendees are not already aware of it. So it's all from a developer perspective, nothing too deep in the technical components for now. So how does a developer engage a serverless platform? So first of all, you write your code function. In this case, a simple JavaScript function of hello world. All it does is receive some parameters and return some value. The only difference when working with serverless platform is that it typically imposes some structure on the parameters. In the case of OpenWhisk, it's a JSON input and a JSON output. Then the important step is deploying this code function as a serverless function. In OpenWhisk, it's called an action. So there is a command line for OpenWhisk that allows us to take this code function, which is just code, and convert it into a serverless entity, which is the serverless function, and we give it a name. So we take the hello.js and convert it into a serverless function called hello. Once it is there, it can be invoked just like any other function. So we can invoke it directly, but more importantly, we can also bind it to an event. To that end, we create an event trigger. You can think of an event trigger as some kind of a pub sub channel with a name. Okay, so that functions are subscribed to. So every time an event is triggered, all the functions that are subscribed to the event are triggered and do their computation in response. So once we have that trigger, we bind the serverless function to the event using a rule. So we created a trigger, my trigger. We bind hello to my trigger using a new rule that we create, which is my rule. And that's it, basically. Every time that event will be triggered using the REST API or CLI of OpenWhisk, then the function will respond by computing using the payload of the event as parameters, and the result, well, in this case, it does compute the results, and of course the result is not really needed, just the computation when responding to an event, because there is no caller. But in any way, you would be able to see the result in the OpenWhisk logs. One other important thing that comes to mind when working events and demonstrates the simplicity of working with a serverless platform is auto-scaling, which means no matter how many events are created, even concurrently, the platform is guaranteed to spawn enough instances of the function to respond to each event independently. So, based on this very quick crash course in serverless, what is the value that we learned from using serverless when employing serverless as a foundation for class analytics in class? So there are quite a few advantages. It's event-driven, and since class computation, as I showed you in the workflow, is basically an event-driven, or it's a continuous flow of events of data objects. So it's a very good fit. It also allows direct invocation. We have the auto scaling, which really simplifies. You don't need to handle, from an application perspective, the deployment of multiple instances in response to multiple events. The function instances are isolated, which means you can also deploy it on a shared infrastructure on a commercial cloud as well as on the edge. The platform overhead is quite light, which means it can fit as well on edge on limited resources as well as on the cloud. One very strong advantage of it is that it's polyglot. It supports by nature different programming languages and different frameworks, so you can mash up your application from different components written in different programming languages. You can mix Python with Java, with JavaScript, with C, and everything will work together because these functions interact through the serverless protocol, and they can work with different backends, different engines, with a neural network, as well as with litops and with comps. And one final advantage that really plays well into the productivity goal of class is that it allows rapid prototyping. You start only with one flow, and then you extend it, you add additional flows, you continue connecting functions and events, and you get to your finished application. On the other hand, we realized quite a few issues when it comes to working with serverless in class. One issue is statelessness. What a platform does in response to an event or invocation, it simply spawns a new function out of the blue. So when this happens, the new function starts just by running code, but it needs the context of the application, the data, the global state so far. How do we do that? So a state is retrieved by either the parameters passed through the event or the invocation, or from the data backbone of class, which is data clay. These are also the two common methods of mitigating statelessness in serverless. The other issues that pertain specifically, for example, to real-time is initialization and finalization overhead. As I said, functions are spawned inside containers. When they are spawned, a container first needs to be created and then populated with code. This and then once the function starts happening, or starts executing, there is also the overhead of business logic. Okay, business logic initialization, such as getting connections and all that. So how do we skip all that? This is called in general a notion of a cold start. How do we mitigate that? We manually integrate into class some warm-up rounds that allow us to use a feature, a typical feature of serverless platforms, which is called the warm start. How does that work? The idea is that after each function container, once it's done executing a particular invocation, remains in memory for a certain additional time, so that if an invocation is needed again, it will already use the initialized container and function. This is called warm start. So we leverage that quite a bit. Another thing to avoid finalization overhead is to use asynchronous execution, where we use the result when it is ready and not waiting for the entire computation to complete. This is done, for example, in LitOps. One final issue that we saw in serverless platform is that we don't have control over scheduling and scale. The scheduling is what you get from the serverless platform, and the scale, for example, the number of concurrent functions, is also dictated by configuration. This we solved using manual tuning. The issue of scale, for example, you don't want to allow too many concurrent functions more than resources you have, because that might create a CPU bottleneck and get you to deadline violation. So we limit the scope of concurrency using manual configuration, and we also avoid the issue of scheduling mostly by leveraging warm start, which also removes the overhead caused by delayed scheduling. One other topic I want to show you is one of the backends. You already saw comps. I want to talk a little about LitOps. LitOps is a map reduce engine. It's a Python library. It's available. It's open source, available in the cloud. I will later put the link in the chat. It's very easy to use, and the idea there is that you can simply span your computation to much larger scale using a compute backend such as a serverless platform. So basically, it provides you with two functions. There is a map, and there is a reduce. Map applies the function to every element of a given function parameter to every element of the given data set, yielding a new data set, whereas reduce applies the function to all the elements of the given data set, but with an accumulator, typically yielding a single result, but sometimes a data set of a different size. The idea of employing LitOps in class is that you increase the parallelism to reduce the total latency for massively computed workloads, such as in the case of trajectory computation and a collision detection, where you have a large number of relatively small and independent computations. So how does LitOps work? Basically, you have the client code, and what the client code does is call either the map or the reduce. What happens then is that LitOps simply takes the map function, and by executing it, it simply dispatches a serverless working function invocation for each element in the dataset. So if the number of concurrent functions that is allowed by the platform is, let's say, 4, then this is essentially the behavior you get. What we did is we took this behavior and we sped it up significantly. I can give you an example. One intersection in Modena, we have a workload of about 21 detected objects. The original computation in the vanilla LitOps took about 4,000 milliseconds. We sped it up to around 350 milliseconds, which is much more acceptable in terms of reaction time for the car. That's about almost 12 times as faster. How did we do that? First, we sped up the data preparation. Part of it was optimizing the data preparation algorithm internal to LitOps, but part of it was also working with the data clay team of PSC, which significantly improved their own mechanism for retrieving the data that is needed for the computation. We also optimized the protocol by which LitOps communicates with its workers, both for sending parameters and for getting them back. The original protocol was based on mediation through object storage, which turned out to be much less scalable and quite bulky, quite slow. We replaced it with direct invocations where possible, and with using a message queue for the return value, a much faster message queue than the object storage. As I mentioned earlier, we leverage extensively the warm start effect of serverless. And one final speed up I would like to highlight is using chunking. As you can see, when you send a separate invocation for each element in the data set, you get the cost of worker, the function reinitialization in between. That is, the function needs to first finalize the previous call, the previous invocation, and then do even a partial initialization for the next call. By chunking multiple elements together, we mitigate this very aggressively and significantly reduce the overhead of finalization and initialization, and thereby getting to this significant speed up. One final topic I would like to talk about is how the class analytics spans both cloud and edge. But originally, all the creatures we were using are cloud creatures, but so we use LitOps, we use serverless, we use Docker, but these elements also exist in edge nodes or in edge clusters, for example, in the case of 5G deployments. How do we allow class analytics to span quite easily to both the cloud and edge nodes? So the idea here is to use federation. What is federation? Essentially, federation is a mechanism that we implemented on top of OpenWhisk that allows to propagate software assets from one OpenWhisk asset that we have in the cloud that we designate as the leader, that's the source of truth, to other OpenWhisk instances that run in other elements that are only loosely connected. And these could be the edge nodes. Now, this makes basically the edge nodes programmable agents of the leader, because we can send different tasks, different computation tasks to them to execute and update those software assets that are running them continuously. Okay, the propagation consistency is eventual, and I can discuss this a little bit later. But the idea, of course, is to overcome delays and partial disconnections. And the main use case in class is, of course, to deploy or to update software, for example, in the street nodes or in the car, even in the cars themselves or in the smart cameras. So one actual use case we use federation is, for example, to deploy the detector on street nodes. A detector is a long-running stateful Docker service that is developed as part of the collision avoidance solution by Unimore, and it is a Docker service. So it's not really an OpenWhisk asset, yet we were able to use the federation mechanism to propagate it just as well. How did we do that? The idea is actually very simple. Every time we need to update or even deploy the first version of the service in an edge node, we simply push the updated version to a Docker registry here that we see here. This Docker registry contains now a new version with a new tag. Then we prepare something called a project manifest. This is part of the federation command. It prepares a new project manifest that contains the tag of the new version. And this manifest is an OpenWhisk element, and it is propagated to the edges. Then at each edge, we have, as part of the federation mechanism, we have a periodical OpenWhisk action that is bound to a timer event, wakes up every time. Now it detects there is a new manifest with a new included task and with a new included tag, and then it handles the service replacement by first pulling the new image and then gracefully shutting down the existing service and then starting the service from the new version. To summarize the class analytics, in this presentation, there were mainly three highlights. First, the use of serverless as the foundation of the class analytics fabric. It's event-driven, polyglot, auto-scaling, simple, and highly productive. But it presented some challenges, such as statelessness and the initialization, finalization overhead that we needed to mitigate. We demonstrated one backend that leverages parallelism to reduce latency for independent computation. You also saw in Ellie's previous presentation a similar concept also employed in comps, another analytics backend. And I showed you I talked about how class analytics spans both cloud and edge using federation. That's it. Thank you, everyone.
Thanks, Ereth. Thank you very much for your presentation. And we can go ahead with the last presentation for today. That is by Roberto Caviccioli from Unimore. Roberto.
Hi, everyone. I hope you can see my screen.
Yes, perfect.
Okay, great. So thank you, Nicoletta. And hi, everyone, and thanks for joining. I will now introduce the MASA infrastructure in which the class project is developing the software architecture. Then I will briefly describe one of the use cases, which is the most complex with respect to the real-time constraint that we need to meet in the class project. And finally, I will present some of the data analytics that are deployed on the compute continuum. Then, the infrastructure. The MASA area is here depicted on the left. It is a metropolitan area behind the Modena train station. There are schools, an health center, a library, a shopping mall, and a startup incubator. All the area is infrastructured with optical fiber for high throughput and low latency communication. And there is also a 4G private network that is used in the project, and a prototype of 5G antenna and a lot of traditional cameras. And we are also deploying smart cameras. As of now, as Ellie described, we are monitoring 16 traditional cameras in our FOB nodes, but we are installing 12 double optic smart cameras. So the coverage of the area will be increased. The more powerful edge nodes, as you can see here, and the cloud servers are located in the area in the newly built data center. Within the area, we drive 3 smart vehicles, which are fully equipped with sensors to perceive the environment and send metadata to our infrastructure. Each vehicle is equipped with 6 cameras, 3 radars, and 1 360-degree LiDAR for a complete view of the environment. For a good precision, for the positioning, we use a high-end GPS sensor. All these sensing data are processed by means of an automotive-grade compute platform. In particular, for this version of the vehicle, we have an NVIDIA Driver GX Pegasus, 1 Auster LiDAR, 6 Seconix camera, and an Xsense GPS. The radars are the only ones that are already installed in the car, and we can read the data through the CAN bus of the infrastructure. And to communicate with the private 4G network, we use an LTE router that is connected to the board. The amount of data that is created from these sensors is very huge. Just to understand the amount, let's say that 5 minutes of LiDAR data is around 12 gigabytes and more, if you consider also the cameras. Let's now discuss the most complex use case that we have to take on this project. The target here is to have real-time obstacle detection, as already described, and also collision prediction that will send warning signals to the smart vehicles and also to connected vehicles. Just to clarify, a connected vehicle is just a vehicle with a GPS and a small embedded board that is able to connect to our private 4G network. And since the software infrastructure is scalable, as shown previously, we imagined 5 different scenarios in which the road users might be in need of external help. We called this the virtual mirror and the 2 sources of attention use cases. Let's dig a bit into it. The scenario 2, which is the one that has been already almost described by Eduardo, is an example of the virtual mirror situation. It means that the class software architecture is able to create a digital twin of the city and provide a look around the corner feel to our users. In this case, the smart car, therefore a fully sensorized one, is in the process of overtaking the garbage collector truck. And in front of the truck, there is a pedestrian that is going to cross the street. The sensors of the car, even if they are fully sensorized, are not able to perceive the pedestrian because it is occluded by the truck. But the city cameras, as you can see here, have a free view of the scene, and therefore the infrastructure can send an alert to the car. The fifth scenario, on the other hand, is what we describe as the two sources of attention. Here we have a connected vehicle which is exiting the parking lot behind the train station and entering the traffic. On the right, there is a roundabout with a pedestrian that is crossing on the zebra stripes, while on the left, a vehicle is approaching. The glance of the driver might be focusing only on the pedestrian or only on the left coming car. Then an alert can be raised from the city infrastructure to the connected vehicle, informing that a collision might appear due to the near road user behavior. Now I would like to describe more in detail the analytics that is distributed over the computer continuum. The detection of the object is performed by means of a DNN, or a deep neural network, on each camera, from what we obtain the corresponding bounding boxes. Then we convert the lower middle point of the bounding boxes to the corresponding GPS position by means of an homography that is computed for each camera. Finally, the GPS position is converted to meters to permit the computation of the speed and the orientation from the tracker that we deploy. We had to benchmark different versions of the object detection network, since our need is dual. We would like the highest precision in detecting the road users while maintaining the latency requirements. We therefore trained different versions of the state-of-the-art YOLO object detection network, with different dataset as well. In particular, the COCO dataset and the Berkeley dataset. Depending on the level in the compute continuum and therefore of the computational power that we have available, we can tune and choose the version of the network. If we want to work in full precision or half precision, depending on which version of the camera and the precision of the camera we have, and so on. After the detection, we then have to track the object to assess its speed. We filter objects depending on their GPS position using a nearest neighbor technique implemented by means of a KD tree. Then we fed an external Kalman filter to filter the noisy data, because every time we detect that there can be noise in the bounding box size and position, and to predict the state of the road user. Since the Kalman filter is a very lightweight computational requirement, we can have a tracker and update a tracker for each object that we have in the area. Here, hoping that you can see clearly even in remote connection, we have a video of what is the camera is seeing. There is the detection of each and the tracking of each object. If the trajectory that you can see and changes color means that the object has been lost, let's say, by the camera for a couple of frames and then reacquired. And therefore, the tracking can be re-enhanced. But the trajectories that are here are the one computed by the Kalman filter, not by the trajectory prediction, because these are the past trajectories. The trajectory prediction will compute the future prediction of each road user. And here, you can see a bird view of the same area, with only the trajectory of the road users depicted, as you can see. Here the area is limited, but the same knowledge that we have from that camera is obtained from all the cameras and the connected vehicles that we have in the area. So thank you very much for attending, and if you have any questions, we are glad to answer.
Thank you. Thanks, Roberto. That was great. Thanks very much. So yeah, I just wanted again to thank all our speakers for your presentations. Thanks very much. And of course, our attendees for attending our webinar today. We hope you have enjoyed it, and just stay tuned. Really, you can check our website and our social media and get in touch with us if you have any questions about the class project. We are now going through the final phase of the project, so we are finishing it at the end of June. So we will have a lot of activities coming up our final dissemination activities and technical activities. So just stay tuned. And yeah, thanks very much for attending. Just remember the full recording and presentation slides will be on our website and on the HiPEAC website as well. Thank you all.
Thank you very much.
Thank you.
Bye-bye.
Thank you.
Thank you. Bye.